Imagine, if you were, the ultimate digital nightmare. You need to move a truly staggering amount of data, let's say 20 terabytes of images.
Wow, 20 terabytes. That's a lot.
It is. But here's the real kicker. It's not just across the internet. It's between two machines. Neither has a static public IP address.
Okay, that's hurdle number one.
Yeah.
No easy way to connect directly.
Exactly. And both are tucked away behind entirely different private networks.
So different firewalls, different NATs.
Yeah.
Tricky.
You got it. And to top it all off, you have to keep the costs, especially cloud transfer fees, incredibly low. Sounds like a mission impossible, right?
And certainly sounds like a massive headache, yeah.
Yep.
Plus connectivity, security too, I imagine.
Absolutely. Well, this wasn't some theoretical exercise. It was a real-world client challenge that sparked this deep dive.
Ah, so this actually happened.
It did. Our client needed to transfer about 20 terabytes of images from a remote machine in one city to their office system in another. And those core constraints were non-negotiable. No static public IPs on either end, completely different private networks, and a crucial need for extreme cost effectiveness.
Wow. Secure, fast, and cheap. The trifecta.
Precisely. The mission was clear. Make it secure, make it fast, and make it surprisingly affordable.
Okay, I'm hooked. How did they pull it off?
So our goal today is to unpack the truly ingenious, custom-built solution this team devised. We're going to explore how they expertly navigated those major technical hurdles and budget limitations,
Sounds good.
ultimately creating a seamless, high-speed, and secure transfer method.
Can't wait to hear it.
When you first hear about a challenge like this, your mind probably jumps to the obvious tools, right? The ready-made solutions.
Yeah, definitely. You think about what's already out there.
So what were some of those common approaches that first came to mind for this kind of large-scale cross-network transfer? And why didn't they fit the bill here?
That's right. The immediate thought for connecting two systems behind private networks, especially without static IPs, often goes to ready-made tunneling services.
Makes sense.
So naturally, tools like Mingrok or Cloudflare Tunnel were indeed considered. They're excellent for many everyday use cases, providing that crucial connection.
But this wasn't an everyday case, was it?
No, not at all. What's crucial here is that for a massive 20 terabyte transfer, those off-the-shelf solutions quickly ran into a brick wall.
How so?
Well, they come with inherent traffic limits or pricing models that, when scaled up for such an enormous amount of data, would have made the transfer prohibitively expensive.
Ah, the cost factor again.
Exactly. Or just incredibly slow due to throttling,
Yeah.
It became clear very quickly that this wasn't a problem a ready-made solution could solve effectively.
So they needed something custom.
It demanded something tailor-made, yeah.
So having quickly hit a wall with the easy buttons, the team was truly back at square one. How do you even begin to build something custom that solves a problem this complex?
Well, first you accept the off-the-shelf stuff isn't going to work.
Right.
What was the foundational idea they landed on to get started?
What was the core concept?
Precisely. This highlights a powerful principle. Sometimes the most effective solution isn't about adapting an existing tool, but about building something purpose-built.
Okay.
Their foundational idea was to create a custom tunnel-like setup using a cloud virtual machine, or VM, as an intermediate server.
An intermediary in the cloud.
Exactly. This VM became the central hub for the entire operation.
Okay, so like a meeting point.
Kind of. The truly ingenious part is how they structured it as a three-part system.
3 parts.
Yeah. You have the uploader program running on the remote machine where the images originated.
The source machine.
Right. Then you have that intermediate server, which was an Azure VM.
The cloud hub.
And then the downloader program on the Office system, the receiving end.
Sender, hub, receiver. Got it.
But here's the crucial strategic move for cost efficiency. The server didn't act as temporary storage, where files would just sit and rack up storage fees.
So it wasn't like Dropbox or S3.
Not at all. Instead, it behaved like a pipe or a proxy, streaming data simultaneously between both ends.
Streaming.
Yeah.
So data flows through it, not to it.
Precisely. Once the stream finished for a file, no file was stored permanently on the VM.
And that was key for costs.
Absolutely key to keeping cloud storage costs at zero.
That pipe approach isn't just clever, it's a fundamental shift in thinking for massive data transfers, isn't it?
It really is. You're prioritizing flow over static storage.
Which fundamentally rewrites the cost equation.
Completely.
Let's dive into each component then. Starting at the source, on that remote machine where all these images are sitting, what exactly is this uploader program doing to get the data moving?
Okay, the uploader. This is where the critical work starts in the remote end.
Yeah.
Its core function is to compress and securely send image files to that intermediate server.
Compression helps with speed and cost too, I guess?
Definitely. And it uses a resumable upload method.
Ah, that's important. Why?
Well, it's absolutely vital for huge files and, potentially flaky internet connections. Imagine if your Wi-Fi drops halfway through sending a 10 gigabyte file.
Oh man, starting over. Nightmare fuel.
Exactly. Without resumable uploads, you'd have to start all over. This method lets you pick up exactly where you left off. Saves immense time and frustration.
Smart. So it's robust.
Very robust. This program was designed for maximum reliability. Think of like a meticulous multitasking librarian.
Okay.
It intelligently monitors the specific image folders, like Images Caminito, instantly noticing new files, JPEGs, PNGs, whatever.
So it watches for new arrival.
Right. But it's also incredibly patient. It performs file stability checks
Stability checks. What for?
to make sure a file isn't still being written to by whatever generated it, like a camera system. You don't want to upload half a file.
Oh, prevents corrupted or incomplete transfers. Good thinking.
Yep. It waits a tiny bit, checks again, maybe 15 times with like a 0.3 second delay between checks, just to be sure it's settled.
And then
When it queues it up, and to keep things speedy, it handles several images at once using threads. I think they set it to 5 concurrent uploads.
so it's multitasking.
Exactly. Carefully managing its workload so nothing gets missed or corrupted. And of course, it also has built-in retry logic.
For uploads that fail.
For uploads, yeah. Maybe 3 retries with a 5-second delay, but also for safely removing files after a successful transfer is confirmed.
Oh, so it cleans up after itself too.
Yep. Ensuring data integrity and local cleanup. Even the removal has retries, maybe 5 times, just in case there's a temporary lock or something.
That sounds incredibly robust and well thought out. Really covers the bases on the sending end.
It had to be.
Now let's talk about the Azure VM in the middle. This intermediate server is truly critical, not just as a pipe, but for controlling costs. How did they configure it to be so financially optimized?
All right, the VM. This highlights a crucial lesson in cloud architecture. The strategic choice of Azure was entirely deliberate for cost optimization.
Why Azure specifically?
What's fascinating here is that ingress, meaning uploading data to Azure, is completely free.
Uploads are free.
Okay. Yeah. Egress downloading data from Azure is where charges apply, but only once, when the Office system fetches the files.
Ah, so you only pay for the data leaving Azure to its final destination.
Exactly. This design meant the client wasn't paying for data being stored in cloud storage like S3 or Azure Blob Storage.
Which would have been astronomical for 20 terabytes.
Astronomical.
What?
And they only incurred charges for the egress bandwidth. This dramatically reduced the overall expenditure compared to traditional cloud storage solutions.
So it's all about optimizing for the cloud provider's specific cost model. Very clever.
Very. You have to know where the costs lie.
And what was running on this VM, the software part?
The server itself runs a Flask application, imageserver.py. Its functionalities are quite specific.
Wait, what?
Securely handling uploads from specific known camera IDs, providing a list of available files for a given camera, and then serving those files for download.
So it manages the traffic flow?
Yes. And crucially, it manages file deletion once downloads are confirmed by the Office system.
Closing the loop.
Right. And to make sure nothing gets tangled, especially when multiple files are being handled potentially from the uploader and downloader at once, they used a threading lock.
A lock.
Imagine it like a single lane bridge. Only one critical file operation, like adding to the list or deleting, can happen at a time for a specific file path. Ensures everything goes smoothly without race conditions, even with lots of activity.
Thread safety. Important.
Very. And to make it accessible easily and securely, Nginx sits in front of the Flask app.
A reverse proxy.
Exactly. Acting as a proxy to handle requests over standard web ports like 80 or 443, maybe with SSL for encryption. This hides the direct Flask port, like 5000, adds a layer of security, and handles connections efficiently.
Okay, that's a truly ingenious setup for the server. Handles the core communication, the security, and the cost optimization.
It is the linchpin.
But for all this data to actually arrive and be useful, the receiving end, the Office system, has to be just as smart. How did they ensure that with 20 terabytes coming in, nothing was missed, nothing was corrupted, and everything was perfectly organized?
Right, the downloader program, downloader.py. This is the diligent receiver on the Office system, making sure every single byte finds its proper home.
So what does it do?
It connects to the intermediate server, asks what files you have for me, fetches them as they arrive.
Pulling the data through the pipe.
Exactly. And then, crucially, signals the server to clean up that specific file after it's been successfully received and verified.
How does it avoid downloading the same file twice if there's a hiccup?
Good question. To prevent redundant transfers, it maintains a local database. They use SCLite3 for simplicity.
A small local database.
Yeah, a table called downloaded files that tracks every successfully downloaded file. It records a camera ID, the file name, and a unique digital fingerprint, a hash.
A hash? For what?
For data integrity. After it downloads a file, it calculates a SHA-256 hash of that file.
Like a checksum.
Precisely. It's like giving the file a unique digital ID card and then maybe comparing it later if needed, or just ensuring the download wasn't corrupted during transit. The database primarily uses the file name and camera ID to track completion, though.
So it knows what it already has.
Yep. Before trying to download, it checks the database. If the file's already listed, it skips it.
Smart. What about download reliability?
The download logic itself is incredibly robust, again with multiple retries, maybe 3 retries, 5 seconds apart if a download fails.
And where does it save the files?
It downloads files to a temporary .tmp file first in the target directory.
Why temporary?
So only after a successful and complete download does it perform an atomic move to the final desired file name, removing the .tmp extension.
Atomic move.
Think of an atomic move like flipping a light switch. It's either fully on or fully off at the OS level. There's no in-between state where you might see a partially moved or corrupted file if something crashed mid-operation. It ensures data integrity, even if the system hiccups during that final rename.
That adds another layer of safety.
Definitely. Furthermore, its multi-threaded architecture allows for highly concurrent downloads. They use a thread pool executor with, I think, 20 workers.
20 downloads at once. That would speed things up considerably.
Hugely. It means it can fetch many files at the same time, significantly boosting the overall transfer speed.
And the cleanup signal to the server, when does that happen?
And here's the absolute critical step. The downloader tells the server to delete a file only after a successful download and the local atomic move is complete.
Ensuring no data is lost prematurely.
Exactly. Data safety was paramount.
So after all this bespoke engineering, getting around network complexities and budget limitations, what were the final quantifiable wins for the client? How did they turn that digital nightmare into a success story?
The outcome was truly triumphant, yeah. It transformed a daunting challenge into a, well, pretty seamless operation.
What were the key results?
First, the core constraint was eliminated. No static public IP addresses were needed on either end. Connectivity just worked, thanks to the intermediate VM.
Big win right there.
Huge. Second, a major win for the cost-conscious client. They faced 0 cloud storage bills. No S3 fees, no Azure Blob fees.
Just the VM cost and the egress traffic?
Exactly. They only paid for the highly optimized egress costs from Azure, which, as we discussed, was strategically chosen for this exact reason. Minimal cloud spend.
Fantastic. And the speed, was it fast enough?
And if we connect this to the bigger picture, the multi-threaded design across all 3 components,
Yeah.
the uploader, the intermediate server handling requests, and especially the downloader, was the absolute key to scaling this solution.
Everything working in parallel.
Exactly. It dramatically improved the initial, potentially slow transfer rates you might expect, enabling the smooth, secure, and ultimately complete movement of all 20 terabytes in a reasonable time frame.
So it wasn't just possible, it was efficient.
It truly was a testament to purpose-built engineering. It really showed how tailoring a solution can overcome seemingly insurmountable obstacles.
What a remarkable accomplishment, taking a daunting, expensive, and technically complex data transfer challenge and transforming it into a seamless, secure, and incredibly cost-effective operation through clever, custom engineering.
It really was impressive.
It really wasn't about trying to force-fit an existing tool, was it? It was about building precisely what was needed from the ground up.
Absolutely. Understanding the constraints and engineering specifically for them.
So, thinking beyond this specific case,
Yeah.
this deep dive wasn't just about moving files, This bespoke solution tells us something profound about the power of custom software development versus relying solely on off-the-shelf solutions, especially when you're faced with unique or highly constrained problems.
That's a great point. Sometimes the standard tools just don't fit the corners you need them to.
Right. So the final thought for you, the listener, is this. How might this approach influence how you think about optimizing for specific limitations, whether it's cost, network access, or massive scale in your own data or tech challenges?
When does building custom become not just viable, but actually the smarter choice. Food for thought.